So hi everyone, I'm Han. So currently assistant professor in geophysics from University of Iowa. So today I'm going to talk about some of my research on the electrical magnetic modeling and some combined with AI tools to help with the critical minerals explorations. Okay. Yeah, so today's topic mostly about on the deep critical minerals. So why we need deep critical minerals? Because we know there are some conclusions from this paper, like we have depletion of surface and near surface mineral resources. And also we found some critical minerals are mainly in very deep areas. And also there are potentially lower environmental footprints of deep critical minerals. And but deep critical minerals is challenges because we know that we cannot see it directly like the near surface minerals. So we cannot see it directly. How can we find it? One of the promising ways is the geophysical tools. So what is geophysics? To people who are not very familiar with this method, it's kind of just use non-invasive physical method to detect subsurface, just like in hospital when you do the CT scan, like they use X-ray as a physical signal, and they provide you the body images, very beautiful body images. And at geophysics, we CT the Earth, so we use different physical signals to image the subsurface. For example, the gravity, if subsurface density is different, they will induce different gravity signal. And we can also use like a seismic waves to travel past the subsurface and provide the seismic velocity images of the subsurface. Similar for the magnetic and or electrical method, they can provide you different subsurface property images. So today's topic is about the electromagnetic method. So it's basically use the electrical magnetic physical theory. So we basically use the EM waves. We can use from like a natural source, like from the lightning, or we can also induce EM waves with like a control source with some electrical systems built in. So after we have EM signals, it will pass through the subsurface. Because in the subsurface, different geomaterials, they have different resistivity, as shown in the right side figures. And the different resistivity, they will translate EM wave signals in the subsurface. And after they come back to the surface, we can collect them either in surface or with airborne surface. So from what we collected the EM signals, it contains all the resistive information of the subsurface. Then we can provide the resistive image of all the subsurface. So this is how EM method work. So, but the EM method also have many challenges. Like we said, we collect lots of signal in the surface. So those surface signal contains like a subsurface information, but like the surface data is very limited, and sometimes it's also very noisy. So we need to find the best like a subsurface resistivity images like shown below to fit the what we observe the data in the surface. So this process we call it inversion in math. So the inversion is always have problem. We have different resistive models. They can all fit what we observe in the surface. So there are lots of uncertainty. We don't know which one to choose. Another challenge is that what we get from the electromagnetic method is a resistivity model. It's actually not a geological model. So that's another problem. So for example, when we found like a low resistivity in our subsurface resistivity models, we don't know whether it's a clay or water or other geomaterials. So it highly depends on the expert's experience in local geology. So there are also lots of uncertainty on that. It's highly rely on the person who understands the geology model in local and how they do the interpretation of the resistive model to geology model. So that's another uncertainty. So people now think about, now we all know like AI is very popular and it solves lots of many problems, and we also trying to use like AI method to solve the challenges in geophysics. So here just two simple examples related to our work. One example is using a convolutional neural network to do image like a recognition in the, like for example in the figures, like they will tell you which one is dog and which one is cat. Use this kind of neural network, just like our brain can recognize them. And another example is the recommendation systems, like just we watch YouTube. After you watch some YouTube videos, it recommend you more videos based on your interest, because you are in a big data set. So there are two examples. So how can we use these two AI examples into the geophysics and help with expand the geophysical data and improve geophysical data? So here is one example. How we use it. It's just the current application in EM method. So one example is that they use the AI to help the signal processing to remove noisy signals, and all accelerate the physical forward modeling to help us with the faster simulations. So here's a more detailed example about inversion. Just we mentioned the challenge, like there are a lot of inversion uncertainty. So here's an example from the other researcher. They generate a lot of synthetic training data sets, just like showing the figures in the left. And they just combine a lot of cubicles in the subsurface, and they generate like a resistivity models to represent subsurface. Then they use one of UNets. UNets is one of the convolutional neural network, which is very popular in the CT image processes. So they just transform CT image to geophysical images to have immersion, to help with immersion. But the problem of this kind of approach is they generate all these data sets synthetically. So those are not very realistic in the really subsurface. But we all know that data is the key in the AI training. So that's why now a lot of big tech companies, they trying to get more and more high quality data sets. So this is a big gap for the AI training in the geophysics. So one of my students, we trying to build more realistic EM and geological data sets to help the AI training. So we just our approach is like first we collect lots of geological data sets from the published papers or materials, and we digitize all these geological models, and then we collect a lot of them, about hundreds from all the papers and materials from all over the world, like showing the right figures, and then next step we convert those realistic geological models to the resistivity models what we need in the electromagnetic simulations. Then we use a very good simulator to simulate all of these kind of EM responses. So we just build this whole data set we need for training. So after we have this data sets, the realistic geological data sets, we do a similar training as I mentioned the previous method. So we compare with them. So we first still train on the synthetic data sets, because we don't have like a huge real geological data sets in reality. It's impossible. So we still train on the synthetic data sets. But later we use this realistic geological data set to transfer learning from the synthetic model to transfer learning into the real geological models. And we compare with the results. So the up panel is from our new training with the geological realistic data sets. It seems our resistivity model have more clear geological structure and close to our geological model. But the traditional one is they have much not as clear as our models. So this is one example how realistic geological data sets can help our training. So another thing we are trying to do now, I mentioned the second challenge, when we convert the resistivity model or other geophysical model to a geological model, we always need a lot of geological experience. So how can we reduce this reliance on the expert's experience? We're trying to also build AI recommender systems. We first combine our already collected EM data sets and all other geophysical data sets, we can also do that. And also combine the historical exploration results and also historical geological interpretation results or some other borehole information in local for the mineral patterns. We combine all of them. So when we face a new site, we can from the new site collect data to analyze the similar EM signatures and also similar geological contexts. Then we use this kind of new algorithms to analyze, to recommend where the targets or where the high potential zones or the mineral types, because we can find the similar patterns from our historic data sets. This work is still ongoing. We're trying to get more data to put into the database. So these short conclusions, so in our in our work, we're trying to first collect the more and more realistic geophysical, especially EM, data sets with geological models. And we're trying to use this to help us to have better subsurface geophysical images. And we also hope to use these AI models to reduce expert dependence. So the future work, we want to get more high quality data, like from the Earth MRI data sets, like just from the previous talk. Yeah, so that's all about today's talk. Thank you.